Hi, my name is Tate Bamey. I'm in OU's Hydrology and Water Security program, and for my semester research project in hydroclimatology, I am doing a comparative analysis of drought resilience in the upper and lower Blue River basins in southern Oklahoma. So the purpose of this study is to analyze temperature and precipitation conditions within the Blue River watershed to narrow down what drought years we're going to use to find our streamflow values. So we'll take the streamflow values of the Blue River in the upper and lower regions, use the discharge values to develop a flow duration curve for both. We'll use the flow duration curve to compare the median and low flow conditions, and then using those values at the end, we'll evaluate which region had more drought resilience. So just for a quick introduction of the entire Blue River Basin, it is located within south central Oklahoma, and it can be broken up into two distinct basins. The upper basin ends around Caddo area. If you're from around that region, you might know where that is. But these two basins, they can differ a lot in their response to how droughts and pluvial events affect them. So first off, we have the Upper Blue River watershed, and the Upper Blue River is pretty unique in that it overlies the Arbuckle-Simpson aquifer, which is known in large for its karst geology and large amounts of limestone and dolomite. And if you've heard of karst geology, you'll know of its high infiltration, the high groundwater storage, and the high groundwater recharge and surface water recharge that happen in those environments. Another thing that makes the Upper Blue River watershed different from the Lower Blue is the elongated watershed shape. So it doesn't respond as fast to precipitation events as a more circular watershed shape would. And another thing that kind of plays into that watershed shape is the very few tributaries that it has. In this next slide, you'll see here the elongated shape of the watershed, and this orange dot here is the USGS gauge site. That'll make an appearance later on in this presentation. But this main blue stream running through the middle is the Blue River, and this shapefile I use from the OWRB to make this map. It is the major streams in Oklahoma, and as you can see, there's only one other major stream that is within this Upper Blue River watershed. And here is the Lower Blue River watershed. What makes the Lower Blue River watershed different than the Upper Blue River watershed is it doesn't have a groundwater source like the Arbuckle-Simpson does for the Upper Blue River. The Lower Blue River does have the Antlers aquifer underlying it, but the groundwater recharge from the Antlers aquifer is not as strong as the Arbuckle-Simpson aquifer is for the Upper Blue River. This is largely due to the karst environment of the Upper Blue River watershed, while the Lower Blue River has a heavier clay and sandstone presence in that region. Additionally, the circular watershed shape is different from the elongated watershed shape of the Upper Blue River, and this contributes to a faster hydrograph time. Another thing is the numerous tributaries that are present within the Lower Blue River watershed. There are double the amount of major streams in the Lower Blue River watershed. And big elephant in the room is the increasing amount of development in this area. The Lower Blue River watershed is pretty close to Texas, and as many of you may know, Texas is encroaching northward, and it's starting to seem like southern Oklahoma is becoming North Texas with every day. Okay, and here is a map of the lower Blue River watershed. As you can see, more of a circular shape than the elongated upper Blue River watershed. Orange dot is the USGS location in blue that we'll be seeing later. And here we have the major streams going through it. So this middle one here is the Blue River. And then we have these other two major streams, which I do not have the name of. But there are two additional major streams, while the upper Blue River only had one additional major stream within it. Okay, and here we have some climate data for the Blue River watershed. And this climate data was obtained from the NOAA and is from the South Central Climate Zone in Oklahoma. The average annual temperature for the time series of 1895 to 2025, the average temperature was 62.30, the standard deviation 1.18, and on the right there we have the normals for 1901 and 1930 and so on. And it mostly looks as if the temperature has stayed pretty steady. Actually dropped from 31 to 1960 to in 1961, 1990. Dropped less than a degree, but has stayed within that 61, 62 range since 1901. And then next we have the average accumulated precipitation. And the average for every year was 38.07 with a standard deviation 8.40. And if we look at the normals, we can see that the amount of precipitation has went up with every section of normals. So from 1901 1930, the average accumulated precipitation was 36.78 inches, and that has worked its way up to 40.42 in the 1991 to 2020. So here I have some data from the 2011 and 2012 droughts in south central Oklahoma. And up top is the temperature data. And as you can see, in 2011, the temperature was 64, the average temperature was 64.10, and the standardized anomaly was 1.53, meaning it was 1.53 standard deviations away from the average. But the 2012 drought was 2.21 standard deviations above the average temperature. Two really hot years for this region in Oklahoma. And down below, we can see the 2011 accumulated precipitation was 24.22, and 2012 had a bit more rain. It was at 29.24, but still definitely below average. And you can see the standardized anomaly here on the right. The standardized anomaly for the 2011 year was negative 1.65 standard deviations below average, and the 2012 was 1.05 below average, meaning both were pretty dry years in this region of Oklahoma. And not only were they dry, it was also very hot. Okay, and here's a quick visual of the average annual temperatures in south central Oklahoma. And as you can see here, the red boxes with the black X inside are the 2011 and 2012 average annual temperatures in south central Oklahoma. And as you can see, they're not the highest temperatures in this climate region for the time series. But if we go to the next slide, we'll see the average accumulated precipitation in south central Oklahoma, and we'll see the 2011 and 2012 precipitation values for this climate zone. And as you can see, they're pretty low as well, so they match up pretty well with the high temperatures and low precipitation, making up for drought in this region in 2011 and 2012. Now we're on to the stream flow discharge values. And first here we have the Blue River discharge in Connerville, Oklahoma, and you can see the stream flow stays around 40, high 30s cubic feet per second, with some high points around May, November, and December. But for the most part, the stream flow is relatively stable throughout 2011. And here we have the 2012 Blue River discharge values in Connerville, Oklahoma. And it mostly looks the same aside from a few outliers. Here in the early parts of 2012, there is around a 300 CFS discharge event. It goes back down to 200 in this outlier, and then there's one huge one, the elephant in the room, at an event that caused 1,600 cubic feet per second discharge at the Connerville site. It must have been a very heavy rain event. I don't have daily precipitation values, so I'm not able to see the storm that blew in right there, but it had to have been a pretty crazy storm for the discharge values to be that high. Now moving on to the lower Blue River discharges, we have the Blue River in Blue, Oklahoma, and looks pretty similar to the upper Blue River in 2012. A lot more outliers in the Blue, Oklahoma. But if you notice here on the side, these outliers are getting up to around 4,500 cubic feet per second. The discharges are staying pretty low. It looks like they're around zero, but these higher values are getting up to 4,500, and this stream gauge isn't really a stranger to higher discharge values in years that aren't as dry. And let's move on to the 2012 values, and it's kind of the same. There are less outliers like here, but around the same time frame of that 2012 storm at the upper Blue River, the lower Blue River suffered from the same one, and it caused a discharge around 8,000 cubic feet per second. Well, earlier in the year, there was a storm that caused 10,000 and close to 10,000 cubic feet per second discharge in this stream. So you may have noticed already in this presentation, but this stream has two different points where there are USGS gauges, and those two different points have very different drainage areas. And this could impact how much flow it gets, and it could weight the discharge values towards the upper basin for this study. And the way that we're going to try to cancel out the effect that drainage area has is we're going to divide each discharge value by the drainage area of each stream gauge just to get what is called a specific discharge for us to use in the flow duration curve. And that brings me to the next step. The next step in this will be to rank the specific discharge values by percentile and to graph the results. And below here, you can see the drainage area for each stream gauge location. So the Connerville, Oklahoma location has a drainage area of 162 square miles, and the Blue, Oklahoma location has a drainage area of 477. So after ranking the specific discharge values by percentile and plotting them on a flow duration curve, this is the result. On the left here, you can see the red is the lower Blue, and the blue is the upper Blue. Well, the red you can see up here, it has a much higher first percentile, like top 10 percentiles are all way above the upper Blue. But if we zoom in on the parts of this graph that we want to see, really the 50th percentile and above, we'll see there is a massive disparity between the upper Blue River and the lower Blue River's low flow values. So here is the 2012 flow duration curves, and it's very much the same story as the 2011 one. The lower Blue River kind of takes over in the lower percentiles. So your 1 through 10, they're just a lot higher than the upper Blue. But once we zoom in to the graph towards the 50th and above, you'll see the upper Blue River really dominates. And there's just a massive disparity between the specific discharge values between the upper Blue River and the lower Blue River, with the lower Blue River just having very minimal stream flow in these low flow events, while the upper Blue River, while it is 95th or like 90th to 100th percentile flow events for them, it's not as low as the low flow events for the lower Blue River in times of drought like this. And here we have the percentile calculations from the flow duration curve a few slides back. And here I calculated the 95th, 90th, and 50th percentile stream flow values for the specific discharge. And you can see, just from looking, in 2011, the Connerville specific discharge values for the low flow, the Q95, Q90, Q50, they're all very much higher than the low flows for the Blue River discharge in Blue, Oklahoma, which is the lower basin. And just to quantify the difference, I divided the 95th percentiles by each other. So I divided the Connerville Blue River discharge by the Blue River discharge in Blue, Oklahoma, and the 95th percentiles, the Connerville location had a 172 times higher specific discharge than the Blue, Oklahoma location in the lower Blue Basin. And if we move down to the 2012, the difference is not as drastic, but there still is a pretty good difference between the two. The Q95 for Connerville was 0.160, and the Q95 for Blue River in Blue, Oklahoma was 0.007, which made for a almost 25 times higher difference the Connerville location had than the Blue, Oklahoma side. And if we move on to the next slide, this is showing the low flow data, the percentiles, after they've been converted back into just cubic feet per second instead of cubic feet per second per square mile. You can see here that the Connerville location is actually a lot higher than the Blue, Oklahoma location, even without the drainage area being canceled out. The 2012 data also shows a pretty good difference between the two. Only the median values, the Q50, are relatively close, and the Connerville location is still higher than the lower Blue location. One conclusion that can be made from this study is that the upper Blue River Basin wasn't as affected by the droughts in 2011 and 2012, and was more resilient to the drought in both years. This was likely due to the inputs from the Arbuckle-Simpson Aquifer, and the groundwater recharge was able to sustain the river for a longer amount of time. The lower Blue River Basin did not have the same amount of input from the aquifer, and lacked precipitation, didn't receive any overland flow or inflow from its tributaries, and couldn't sustain significant stream flow. That being said, the lower Blue River Basin is home to a lot of development lately, and this drought susceptibility could spell economic impacts in the future if Durant keeps developing like it is. I haven't mentioned it in this study so far, but the Blue River is the primary source of water for the city of Durant and the surrounding suburbs in Durant. One of the limitations for this study was the lack of other years being included. One of the things I hope to accomplish with this study is to incorporate more years and show the difference in how each watershed manages events of heavy rainfall, more long-term wet conditions. Another thing I would like to do is to continue this study by doing base flow recession analyses and measuring the groundwater input in both basins, just to measure the output from both the Arbuckle-Simpson Aquifer and the Antlers Aquifer that underlies the lower Blue River Basin. Here are my sources for this study. I used the NOAA for all of my climate data and the USGS for all of my stream data. The OWRB was used for some shapefiles for the maps included in this study. Lastly, I just want to say thank you for watching. This is my first foray into hydroclimatological / hydrological research on my own. And I'm welcome to any critiques or feedback you may have. So if you have any feedback, please let me know in the comments or whatever. Just thanks for watching.